Welcome back to AI.Code.Cast. Today we're diving deep into a classic coding problem that that often trips people up. It's called finding the missing number.
Ooh, okay.
So picture this. You have an array,
All right.
and it's got a jumbled up sequence of numbers, right?
Okay, got it.
And, they should be all the numbers, like starting from 0 and going all the way up to some limit.
Mm-hmm.
But one sneaky number has gone missing.
Yeah.
And our challenge today is to track down that missing number.
Sounds simple enough. I like it.
Yeah, it sounds deceptively simple, right?
Yeah.
But like many coding puddles, it's a great example of how just a little bit of cleverness can go a long way.
For sure, for sure.
Exactly. And what I think is so fascinating about this is there isn't just one right way to solve this.
Oh, interesting.
We're actually going to explore 4 different approaches today.
Okay.
And each one has its own pros and cons.
I'm excited.
Yeah. So buckle up. It's going to be an exciting deep dive.
I'm ready when you are. Where do we start?
Let's start with the approach that probably just comes to mind first, right? Like the brute force method.
Okay, sure.
It's not always the most elegant,
Right.
but sometimes it helps to just sort of lay all the cards on the table, like what's the most obvious thing we could try?
Yeah, just get a feel for it.
Yeah, exactly.
Okay, so with brute force, we're basically like checking every possible number against our array.
Right.
Yeah.
Exactly. We'd go through each number, from 0 to that upper limit
Mm-hmm.
and see if it's in the array.
Okay.
And if we don't find it, well, we know that's our missing number.
All right, makes sense. But wouldn't that be like incredibly slow?
You're absolutely right.
Especially if you have a really big array?
That's the major drawback of brute force. We're potentially like looking at each element in the array multiple times, right?
Yeah.
So if the array has like 1 million numbers,
Oh, wow.
we could end up doing 1 million checks just for each possible missing number.
Yeah, you're going to be there a while.
Exactly.
Yeah.
So in terms of time complexity, this would be what? Like O of n squared.
Yeah, O of n squared.
Exactly.
Uh-huh.
Because for each number in our range, we're doing a linear scan through the array,
Right.
which is O of n for each number.
Hmm.
So it's a good starting point, just to understand the problem, but we can definitely do better.
Yeah, for sure. So if brute force is kind of like the sledgehammer approach,
Okay.
what's a more delicate tool we could use here?
Well, one strategy that comes to mind is sorting.
Sorting.
Imagine if we could just line up all the numbers in our array, nice and neatly.
Yeah.
Wouldn't it be easy to just spot the missing one then?
Yeah, I can see that.
Right. So if we sort the array,
Yeah.
we could just go through it sequentially.
Right.
And if we find a gap where a number should be, that's got to be our missing number.
Yeah. I like where you're going with this.
Right. Like let's say our array has the numbers 3, 0, and 1.
Okay.
If we sort that, what do we get? 0, 1, 3.
Uh-huh.
Boom. 2 is missing.
Yeah, exactly. It's very clear.
Right. So what do you think about this approach?
I like it. It's definitely a lot more intuitive than the brute force method. And I think it would be like significantly faster too, since we're only going through the array once after we sort it.
Okay, so we've got brute force on the table and sorting on the table. Just to kind of take stock here, what are the key takeaways so far? What are the trade-offs between those two?
Okay, so brute force, easy to understand, easy to implement.
Yeah.
But it gets horribly inefficient with larger data sets.
Yeah.
Because of that O of n squared complexity. Sorting, much faster option, especially for really big arrays. And it has that added benefit, like you said, of the solution being pretty intuitive.
Exactly. But there's a bit of a hidden cost with sorting, isn't there?
You're talking about the complexity of the sorting algorithm itself.
Yes.
You're right. Even the most efficient sorting algorithms generally have a time complexity of n log n, which means that the time it takes to sort grows faster than the number of elements in the array.
Yeah.
So while it's better than O of n squared,
Yeah.
we still got to factor that in.
Right. So sorting is a definite improvement over brute force, but it's not necessarily the most efficient solution overall.
Right.
And there are a couple of other interesting approaches that I think we can explore. You ready to dive into those?
Absolutely. Let's see what other tricks we can find up our sleeve.
Oh, okay. All right. So we've talked about brute force.
Yeah.
And we've talked about sorting. But what if we could find the missing number, without even rearranging the array at all?
Ooh, that would definitely be more efficient. Any ideas?
Well, I was thinking about, data structures that are kind of designed for super fast searching.
Okay.
Something like a hash set.
Ah, hash sets.
Yeah.
I see where you're going with this.
Yeah.
Hash sets are like dictionaries, but for numbers.
Yeah.
We can check if a specific number exists in a hash set, like almost instantly.
Exactly.
Okay.
So we could take all the numbers from our array,
Okay.
put them into a hash set,
All right.
and then we just check each number from 0 up to that limit.
Right.
And if a number's not in our hash set, that's our missing one.
Oh, I love it. It's like a reverse lookup.
Right.
We're not searching for a number in the array. We're searching for the absence of a number.
Exactly.
Right.
And because hash sets are so efficient at checking for membership, we're talking about a much faster approach.
Sure, yeah.
Do you remember what kind of time complexity this gives us?
Yep. This would bring us down to O of n,
Mm-hmm.
because we're basically just doing a linear scan through our range of numbers.
Right.
And then the hash set lookups are considered constant time,
Right, right.
much better than sorting's O of n log n.
Definitely a win for speed. But it's worth noting that there's a trade-off here.
Right.
Yeah.
Hash sets, they require that additional memory, right,
Mm-hmm.
to store those numbers.
Yeah.
So if memory usage is like a big concern for you, this approach, it might not be the best choice.
Okay, so we've explored sorting. We've explored hash sets. Both good options. Depends on whether we're prioritizing speed or memory. But I have a feeling you've got another trick up your sleeve, something a bit more unorthodox.
Ooh, you know me too well.
Yeah.
This next one, it might seem a bit out there,
Okay.
but it's incredibly clever.
Mm-hmm.
Are you ready to dive into the world of bit manipulation?
Bring it on.
Right.
I'm always up for a challenge, especially when it involves, like, bits and bytes.
Okay, let's talk about XOR.
No.
The XOR operator, which we usually represent with the caret symbol, that little hat symbol,
Yeah.
has a very unique property.
Okay.
If you XOR a number with itself, the result is always 0.
Okay, so it's kind of like a self-canceling operation.
Exactly.
What does that have to do with finding our missing number, though?
Okay, well, imagine we XOR all the numbers from 0 to our limit,
Okay.
and we XOR all the numbers in our array, too. What do you think will happen?
All the numbers that are present in both, like, that full range and the array,
Yeah.
they'll get XOR'd twice,
Yeah.
which means they'll cancel themselves out.
Exactly. It's like the duplicates vanish into thin air, and you're just left with the missing number.
Wow, that's pretty brilliant.
It's like magic, but it's just clever math.
I'm starting to see how this bitwise wizardry can be so powerful.
Mm-hmm.
But how does it stack up against, our other approaches in terms of efficiency?
In terms of time complexity, it's also O of n, because we're essentially making 2 passes through the data.
Right.
But the real beauty is its memory efficiency. We're only using a single variable to store that running XOR result.
Mm-hmm.
So the space complexity is O of 1.
So it's as fast as the hash set approach, but uses way less memory.
Exactly.
That's impressive. Are there any potential pitfalls or, like, edge cases that we need to watch out for with this XOR approach?
That's a good question. One thing to keep in mind is that this approach relies on the assumption that all the numbers are distinct.
Okay.
If we had duplicate numbers in the array, the XOR operation, it wouldn't be able to isolate the missing one correctly.
That makes sense.
Yeah.
So it's important to understand, like, the constraints of the problem before we jump into a specific solution. But so far, this XOR method seems like a pretty strong contender.
I agree. But before we declare a winner, I have one more approach to share.
Okay.
And this one takes us back to a story about a brilliant young mathematician named Carl Friedrich Gauss.
Okay, I'm all ears. Tell me about this young Gauss and how he ties into our missing number problem.
Well, the story goes that when Gauss was just a schoolboy, his teacher challenged the class to add up all the numbers from 1 to 100,
Okay.
thinking it would keep them busy for a while.
Right.
But Gauss, being a mathematical prodigy, came up with the answer in seconds.
Wow. I wish I had that kind of mathematical prowess back in school. How did he do it?
Well, he noticed a pattern.
Okay.
Instead of adding the numbers sequentially, he paired them up.
Okay.
Like 1 and 100, 2 and 99, 3 and 98, and so on.
Okay, yeah.
Each pair adds up to 101.
So there are 50 pairs. And 50 times 101 is 5,050.
Exactly.
Very clever. But how does this help us find a missing number?
Well, Gauss's insight led to a formula for calculating the sum of an arithmetic series.
Okay.
The sum of the first n numbers is n times n plus 1 divided by 2.
I'm starting to see the light here. So we can use this formula to figure out what the sum of all the numbers in our array should be if none were missing.
Yes.
And then we just compare that to the actual sum of the numbers in the array.
You got it. The difference between the expected sum and the actual sum is our missing number.
So using Gauss's formula, we can solve this problem with just a bit of arithmetic. No sorting, no hash sets, no bit manipulation required. That's pretty elegant.
It is, isn't it? And in terms of efficiency, it's right up there with the XOR and the hash set approaches.
Yeah. So let's break down the complexity here.
Okay.
We need to iterate through the array
Right.
to calculate the actual sum, so that gives us a time complexity of O of n.
Yep.
And we're just using a couple variables to store the sums, so the space complexity is O of 1.
Spot on. So we have 4 distinct approaches to solve this problem, all with their own strengths and weaknesses. We've got brute force, which is easy but slow.
Right.
Sorting, which is intuitive but has a bit of overhead. Then there's the hash set, which is fast but uses more memory.
Yep.
And finally, we have Gauss's formula, which is elegant, efficient, and just plain cool.
It's amazing how one problem can be tackled from so many different angles. This deep dive has really highlighted the importance of having like a diverse set of problem-solving tools, in your coding arsenal.
Absolutely. Each approach offers a different perspective and a different trade-off. The best choice really just depends on the specific constraints of the problem you're facing.
So to wrap things up, if you're ever faced with the missing number challenge, remember, you have options. Consider the size of your data, the importance of speed versus memory usage, and even, the elegance of the solution.
And most importantly, don't be afraid to think outside the box. Sometimes the most elegant solutions come from the most unexpected places.
That's all the time we have for today's deep dive on AI.Code.Cast. Thanks for joining us, and happy coding.
Until next time.